Okay, so let us start. This will be, first of all, I should definitely thank the organizers for inviting me here. Although I must admit that I have almost nothing to do with high energy physics. So you may treat this first lecture, this free short 1 hour lecture, as an opportunity to extend your general mathematical education, or maybe deepen it, and I assure you that it may come useful at unexpected time. I'm very grateful to Mirela for making it possible for me to come. It is my first time in Romania, of course, also first time in Bucharest, so I'm also learning all the time. Okay, so the topic of our, I hope that it will be possible for you to hear me when I'm sitting, because I would like from time to time to point something show something at my slides, or maybe note something, so it will be easier for me to see it. The topic of my lecture is contact geometry. Contact geometry is a part of very classical differential geometry, which means that we will be studying geometrical structure. Geometrical structure usually consists of a manifold together with something, additional structure, which is usually a vector field or another kind of tensor. You definitely know Riemannian manifolds, which are manifolds with symmetric tensor of special kind. You definitely know symplectic structure, which is a manifold with anti-symmetric tensor with special anti-symmetric two form with special properties, or Poisson manifold. Sometimes it is a manifold with, I don't know, group action, then we speak, which is compatible with the structure of the manifold. So then we speak about Lie groups. So all those examples are examples of so-called geometrical differential geometric structures, and we will be discussing a different kind of structure, namely a manifold together with a certain distribution. This distribution will be usually denoted by C. And before I go into the formal definition, I would like to show you 3 examples, sometimes similar to each other and sometimes very different. Just to let you, just to give you an opportunity to later on think about concrete examples when we will be discussing more general features. So first, let us start with the contact structure on the manifold, which is a product of cotangent bundle to some manifold and real numbers. This manifold has a canonical contact structure, which is of wide use, for example, in partial differential equations theory. And also it is used in classical mechanics. You will see the examples of this application later. So what is this contact structure? So let us look at functions on manifold in a little bit strange maybe way. So instead of thinking of them as functions, let us think of them as sections of trivial bundle. Then we can take first jet prolongation of a function, which means that essentially we are looking at the tangent plane to the graph of the function. And in case when the bundle is trivial, if we take section of trivial bundle with the fiber which is R, the first jet prolongation has very simple structure. It is our future contact manifold. So the first jet consists of a differential and value of the function. And then what I do, I think about all the vectors that are tangent to graphs of prolongations of such functions. So essentially I take any vector tangent to the base, and I use this section, which is the first jet prolongation of the function, to lift this vector up here to the tangent vector to my contact manifold. And then when I get the set of all those vectors, I span the distribution of them. So let us look how this lift looks like. It of course has to project to the original vector, so there is this component coming from the base. Then we can look at the last component, which is just which shows what happens when we change a little bit. When we look around the point, how the function changes around fixed point. So there are those partial derivatives with respect to coordinates, and if we keep the point in the jet space, which means that I keep the differential of the function fixed, and I keep the value fixed, then how this vector is lifted up there depends on the second derivative of the function. So when I change the function, keeping the point fixed, I mean keeping the differential fixed, it means that this can be arbitrary. So this is fixed because I look at vectors attached at certain point of at certain jet. So this is the coordinate of the jet, but this can be arbitrary. So when I span the distribution using these vectors, I finally get to the conclusion that the distribution is spanned by such vector fields. I have n of them. If n is a dimension of Q, I have n vector fields like that in coordinates. And there is also n vertical vectors, and the fact that they are just simple vertical vectors, nothing very fancy, comes from the fact that those two second derivatives can be arbitrary. So as a result, I get a distribution on the product of cotangent bundle and real line. The manifold itself has the dimension 2n plus 1, which is odd number, as you can see, and the distribution has one dimension less. That's the dimension of the whole manifold. In this particular case, this distribution has a name. It is a Cartan distribution on the jet space. It's an instance of Cartan distribution on the jet space. We have also the picture that illustrates how this distribution looks like in case when the manifold is just real numbers. So we think about jets of real functions defined on real numbers. Then our contact manifold is the simplest possible contact manifold, namely R3. And we should think about x as arguments of the function and y as value of the function, and z as value of the function, and y it is the differential of the function. And here you see how those tangent vectors look like when we think about functions that have value 0. So they are only, only tangent planes at points with z equal to 0 drawn here. However, it is of course invariant with respect to moving the whole picture along the z-axis. So this is just a picture to fix your mind on something concrete. What are the features of this Cartan distribution? This is definitely not integrable. When I calculate the Lie bracket between the vertical vector and this vector that is sometimes called horizontal one, I see that the bracket is proportional to d over d z vector, which definitely does not belong to the distribution itself, therefore it is not integrable. Since the distribution has one dimension less than the whole, the distribution, the vector subspace of the tangent bundle at each point has the dimension 1 less than the dimension of the manifold itself, it means that locally we can describe this distribution as a kernel of some one form. And in this particular case, this one form is global. It will not always be the case, but in this case it is global. Since we have here the Cartesian product, this vertical r coordinate is well defined, so dz is definitely global. The component we have here, you can recognize as also a canonical object defined geometrically. It is written here in coordinates, but it has geometric meaning and it is a Liouville form on the cotangent bundle. So summarizing, we have the first simple example, which is the canonical contact structure on the cotangent bundle times R, which is treated as a first jet, the bundle of first jets of functions. And this is one codimensional distribution, non-integrable, being simultaneously a kernel of a globally defined one form. So now we change the setting slightly. So the story will be again about first jets, but the bundle will be a little bit more complicated on one side, but on the other side very simple, because the dimension will be simple. We look at the Möbius strip with this vertical direction being infinite. Usually when you want to make a Möbius strip, you cut a piece of paper, you flip it and glue, yeah? So now think that you have to flip the infinitely wide strip, but the idea is the same. We have integer numbers acting on pairs of real numbers in such a way that the first variable is a little bit translated by 2 pi, which is just chosen for convenience. And whenever we move once by 2 pi, we flip the sign in the vertical direction, dividing R2 over Z. By Z we obtain this B, which is a line bundle over S1, over a circle. A line bundle means that it is a vector bundle with one-dimensional fiber. The linearity, the fact that it is a vector bundle, is granted by the features of this action of Z, which is linear in the second coordinate, and this linearity passes to the equivalence classes, so we have a vector bundle indeed. And again, we will be looking at jets of sections of this bundle. As you probably know, it is enough to have two coordinate charts to describe Möbius strip. So we choose those coordinates charts in such a way that will be convenient for us. First we cut the strip somewhere here, which means that the first variable will change from 0 to pi. And the second variable is, of course, just r. And the second chart we obtained cutting the Mobius strip in different place. And then we will be looking on coordinate changing in the intersection of those two charts. So what is the interesting thing about the intersection is that the intersection is composed on two disjoint parts. So this is this purple part and this green part, and these are not connected. So let us look at the coordinates. We use the q coordinates on the circle, and the vertical coordinates will be called z. And since we are looking at jets, we will also have another pi coordinate, which is responsible for partial not partial, but just the differential along the coordinate q. And again, locally, we have a piece of an interval in R, which is a piece of our circle, and we have value of the function, which is z, and we take first z, so locally it looks as in the previous example, which means that, for example, over this coordinate chart domain, we have the Cartan distribution written as before, however simple, because it is of dimension 2. And over the other chart, we have with primed coordinates, again, a Cartan distribution which looks the same in coordinates as previously. And we have changes of coordinates. So in this purple thing, the coordinates, just the coordinates changes very simple, it is just identity, nothing happens. And over this green part, the coordinates are changed in a sense that q is moved, and coordinates of the jet and value of the section change signs. Oh, because this is how the action works. So let us look what happens with our vectors that span the distribution. Of course, over E. Over this one part of the intersection, nothing happens because we have the identity as coordinate change. So in both coordinates, vectors spanning our distribution look exactly the same. However, over this green part of the intersection, there are changes. So if I want to write this vector belonging to the distribution in primed coordinates, I have to change here sign in here, and of course as a result nothing changes. So this first vector looks again, maybe I will make it bigger, this first vector looks the same whatever coordinates I use, however the vertical vector changes sign. But changing sign, of course, doesn't affect the distribution. This is just a different vector spanning the distribution, and the distribution remains the same. So it shows that the Cartan distribution, although here defined using coordinates, is well defined, and we definitely have a kind of contact manifold. However, when we try to do the same as previously, express this distribution in terms of some forms, which people usually do, because it is a practical rule that working with forms is easier than working with something not that tangible as the distribution, then we see that it is impossible to do it globally. Again, I can write a form in coordinates as previously over one coordinate chart and over the second coordinate chart, and I will see the same expressions. but it turns out to be impossible to glue those forms together to form a global form. Let us see the problem. Of course, the kernel of one form does not change when we multiply the form by function which is non-vanishing. So we can freely play with this form and this form, multiplying it by non-vanishing function. So now imagine that we have a global one form that has the same kernel as our local forms eta O and eta U. Then it should be like that, on one chart, those two forms, this hypothetical global form and this form that we have defined, should be proportional with the coefficient which is non-vanishing function, and the same should happen over U, that we have two forms, this is the global one and this is the local one, and whenever this local one is defined, they should be proportional with some non-vanishing function. Then when we take it on the intersection, those two local forms should be connected with each other, should translate to each other with, again, a function which is a product of the previous functions and is non-vanishing. However, we know how those forms eta O and eta U, how they are related, and they are related by minus sign over the green piece of the intersection, which means that this function should be positive in some places, negative in some other places, and all over it should be continuous. So it is impossible, yeah, because the Mobius strip is a connected manifold. So this time we have obtained again a well-defined distribution. However, this distribution is not a kernel of a global form, and this is the difference, important difference with the previous example. And finally, and here's the guy who is responsible for all those cut papers and simple mathematical demonstrations for children. And also some deep mathematical results. So finally, we can pass to the third and last example for now. This time it will be a projectivized cotangent bundle. So we again take the cotangent bundle to any manifold we like. We remove the zero section from this cotangent bundle, and as in creating a projective space, we define a relation which says that two covectors are equivalent whenever they are proportional. So there is a non-zero real number, this will be real projective space, so non-zero real numbers are such that two covectors are proportional, and our last example of contact manifold will be the quotient space of the space of non-zero covectors divided by this equivalence relation. And this time we will start from the very beginning with defining our distribution by defining local contact forms. And we proceed in coordinates as we do usually while discussing the projective space. For simplicity, I will think about Q equal Rn, but this is just for the sake of the presentation. I don't need to worry about the domain of the coordinates in the very base, so on Q. But we can repeat this procedure as it is with whatever manifold we like. But we start with Rn. So, as usual, we define coordinate domains, and they are numbered. There is as many of them as the dimension of our manifold Q, which is n in this situation, and each coordinate domain contains of all the equivalence classes such that the coordinate of a covector, which is in agreement with the number of the coordinate chart, is not zero. Of course, when we take a sum over all those coordinate chart domains, we will obtain a cover of the whole manifold. Therefore, if we define things in all pieces and then we ensure that they translate to each other properly, then we will have a global thing. So we define projective coordinates also as usual. So within the chart, we keep the base coordinate unchanged, and the covector coordinate is a ratio between the actual coordinate of the covector and the divided by this coordinate of this non-vanishing coordinate, which is non-vanishing within the chart. And here we have our local contact form, which is defined within the chart. So it is again non-vanishing form defined locally on UK. I will want to think about kernels of all those forms. So I need to know how they are expressed in different, so the same form in different coordinate charts, so how they talk to each other. Therefore, of course, I take the intersection of the two coordinate charts. In the intersection, I know that both of momentum coordinates are not zero. Therefore, I can divide by both of them. And I write a coordinate change rule, which is written here. So, of course, Q coordinates, so base coordinates are the same. They do not change. If I want to write pi coordinates in the chart number L by pi coordinates in the chart number K, I again take the ratio. It is easy to see how it is, why it should be like that. And there is this one coordinate left, which was not included here, because here I can calculate this only for j not equal to k and not equal to n. So I should have those additional coordinates, those exceptional in both in those two charts, and they are just the inverse. And then I take a piece of paper and pen, and I carefully, trying not to mix anything, calculate the transformation rule for contact forms, and what I get is that the Lth contact form is proportional to the Kth contact form, and the coefficient of proportionality is a non-vanishing function, because those pi coordinates definitely non-vanish within the intersection of those two charts. So since they are proportional with non-vanishing function, they have the same kernel. Therefore, the kernel is globally defined. So I have, summarizing, I have non-vanishing, on UK, non-vanishing form, which has the kernel, which is the distribution of dimension 2n minus 2. On the intersection, I have proportional forms, so the kernel is the same. Therefore, I can define a global distribution, which will be a contact distribution on the projectivized tangent bundle. As you see, this construction ideologically was simple, but it was tedious to check everything and calculate all those components. So I will be happy if we would be able to give an easier definition of this contact structure, and we will do it in a moment. It might be interesting for you to maybe, I don't know, maybe during tutorial, maybe just on your free time, to see that if we start with not Rn, but if with something simple but not flat completely, as if we start with Q equal to S2, then we can recognize that projectivized cotangent bundle is as a manifold diffeomorphic to S3. So this way we can construct a contact structure on S3. The fibers of projection from the projectivized cotangent bundle to S2 fibers when we project to S2, the fibers are circles, because each tangent space is a two-dimensional vector space, and when we projectivize it, we get RP1, yeah, the one-dimensional projective space, which is isomorphic to a circle. So it is a circle bundle, and we can recognize it that this is precisely the Hopf bundle. So we have this way we can construct a contact structure on the total space of the Hopf vibration. Okay, so let us now pass finally to the formal definition of a contact manifold, which means that we have to collect the features of all those examples and make an abstract sense of how are they similar, or maybe how are they different. And the definition is as follows. A contact manifold is a manifold together with a regular distribution. Regular means that, maybe I will move one slide further. So regular means that it is of constant rank, and this is locally spanned by smooth vector fields, and we have seen it in almost all the examples. I didn't discuss those fields in the third example, but this is also the case. The distribution is of codimension 1, which means that it is always one dimension less than the dimension of the manifold. And there is this third feature that was not very much visible in the examples, which is maximal non-integrability. This we have only pointed out that Cartan distribution in the first case is not integrable, but we didn't discuss it further, so we will discuss it now. Especially we have to define what does it mean to be maximally non-integrable. We know what it means to be integrable. It means that it possesses this distribution like that possesses integral submanifold of the maximal dimension at each point, and we probably know that this is the same as being for regular foliation. It is the same as being involutive. But what is maximally non-integrable? So if it is non-integrable, it does not have this property, but what does it mean? It is maximally integrable. And one way of expressing is to look at the following construction. We have this one codimension distribution. Therefore, point by point, we divide our tangent space by this subspace being a part of the distribution. So what we get here is a one-dimensional vector bundle, which we decided to call a line bundle. So we have a projection, the canonical projection associated to the quotient is a projection from this vector bundle to the line bundle. It respects the linearity, so it is a vector bundle morphism. This is also a bundle over M. And now let us define a certain two form on C only, with values in this line bundle. We will see in a moment that this is really a two form, so it depends only on the arguments on vectors at one point. However, it is easier to define it using local vector fields. So we take two sections of our distribution, so two vector fields that with values belonging to the distribution, and we define our two form in the following way. To apply this to form, what we have to do is to take the bracket, really bracket of those two vector fields, and use the projection. So these have values in the line bundle that I mentioned before here. So let us now check that this is really two form, and so something that depends only on values of my vector field at certain point. Yeah, these are vector fields on M. So it should depend only on the two vectors. How do I do it? Exactly in the same way as when checking that Cartan so-called magic formula works, and it provides us with the two form of one high dimension, which means I multiply one of my vector fields by a function, and I look what happens. So I multiply a vector field by a function, I put it into the bracket. I know that the bracket is a differential operation, therefore it obeys the Leibniz rule, which is written here. So I have to multiply bracket by a function, and I also have to act with one of the vector field on the function and multiply the second function. So this part here depends on the differentials of a function. However, since this function multiplies section of C, then by taking the quotient, and this row here means taking the quotient, this part disappears. And what I get, and I've said that row is linear, therefore with this function here I can go in front of row. So what I get is exactly what I wanted. It means that it is linear with respect to multiplication by functions, which means that I really have a two form anti-symmetric operation with values in a line bundle. And now what in maximal non-integrability means? It means that this two form is non-degenerate on C. It is defined on C, and it has to be non-degenerate on C. So if the distribution is integrable, then this two form will be just zero, because when integrable, the bracket belongs to the distribution, and when I project, I get just zero. And the fact that it is non-degenerate is like just on the other side of the spectrum, it is maximally non-degenerate. From this we can immediately conclude that that C has always to be of even dimension, what we've seen in all the examples, and this of course mean that M is of odd dimension. Sometimes the contact geometry is understood and presented as, say, even dimensional counterpart of symplectic geometry. No, because you know, symplectic manifolds are always of even dimension, contact manifolds are always of odd dimension, and they, as we will see, they have something to do with each other. So people understand the contact geometry as odd dimensional version of symplectic geometry, which in my point of view is not really true. I will try to convince you otherwise. I mean, I will try to convince you that contact geometry is a very special part of symplectic geometry, but it will come in a few minutes. First, let us see, we have seen that in many examples in one example at least, we have seen that the contact distribution is a kernel of a globally defined contact form. So whenever this happens, we call this form, this one form, contact form. So contact form may be local and may be global. And the definition is as follows: the contact form is a such non-vanishing one form that its kernel is a contact distribution. However, we would like to somehow express this maximal non-integrability in such a way that it is expressed only in the language of contact form. Why? No, because people do that. Yeah? Contact forms are widely used, they are useful, so we would like to know their properties. So we have the proposition: a contact form is a contact form. So it's the kernel is a contact distribution whenever a contact form whenever a form satisfies such an equation. And you can immediately see why in the Möbius strip example we were not able to provide a global contact form, because look. We have d eta, which is two form, which is with the power 2 external power n. This part is a 2n form multiplied by eta. It is 2n plus 1 form on 2n plus 1 manifold, which means that it is top form. And if it is non-vanishing, it is a kind of a volume form. And it says that the manifold over which this volume 4 lives is orientable. And the Möbius strip is not orientable, so is the jet bundle. Therefore, there is no chance for having a global contact form there. So let us look at the proof, how we do that. And this will be a construction that will, in a sense, reappear. And we will gain a perspective over this eta, Ni2 form with values in the line bundle that we used for the definition of maximal non-integrability. So imagine we have some open subset over which we got a contact form, and we have this kernel locally defined also in this open subset. Then we can look at the contact form. Okay, so we have the line bundle and we have the dual. The annihilator of the line bundle is the annihilator of the contact distribution is a one-dimensional sub-bundle of the cotangent bundle to our contact manifold. And this is the usual situation in linear algebra. If you have on one side a subset, then on the dual side you have the quotient. Yeah. So here the quotient, here a subbundle, and having a contact form, we have a trivialization of this one-dimensional of this line bundle. So we can, having this eta, we can express our annihilator as locally, of course, so not m but O times r. Maybe not equal, but can be expressed as using the eta. And now what we will do, we will use this eta to define a certain two form on contact distribution, and we will compare this because we already have two form with values on line bundle, so we will compare those two forms. So the definition is as follows. I take my previous two form and I contract it with distinguished section of the dual. In such a way, I obtain a true, in a sense that with real values, true form on the contact distribution. And let us, in a sense, make sense of that. What is that? To see what's that, we take two sections of the contact distribution, and with such property that it has prescribed values at point. Those two sections have prescribed value at point under consideration, and we calculate. As a matter of fact, what we calculate is the eta of small v and small w. However, we use the Cartan formula, and this is why we need those sections. So we just make use of the Cartan formula. Yeah, we act with one vector field on the contraction with the other, then we change the order, and then there is this additional part. Those two components vanish because W and V are in Cartan distribution. So we are left with that. When we really think about what it is the same as contracting eta with our previously defined two form. When we use the fact that this is the dual of that. So we see that our new form, new two form, is almost the differential of eta when we use this trivialization up to a sign. Okay, so this is the conclusion. The differential of eta restricted to the contact distribution coincides with our two form, which is part of the structure, when we trivialize. So from that it follows that since that thing was non-degenerate on C, it follows that the eta is also non-degenerate on C. Therefore, when this non-degeneracy means that if I take the nth external power, I obtain a 2n form which is non-vanishing on C. And there is this one lacking dimension. When I multiply this by eta, eta does not vanishes on vectors in this one lacking dimension. I get something that does not vanish on the whole tangent bundle. So we can see why this is the criterion for checking whether a given form is a contact form, so whether its kernel is a Cartan distribution. Okay, so now after looking at several examples, we can formulating the definition, we can go further. First, let us look at the literature and let us see what concepts and notions are associated to the contact structure. First, there is a very useful theorem, which is a version of the contact version of Darboux theorem. Darboux theorem, the original version says that all symplectic forms look locally the same, that we always can find a coordinate chart such that they look as a symplectic form on a cotangent bundle. And here we have a contact Darboux theorem that says more or less the same. Around each point we can find an open subset, which is a coordinate domain, and a set of coordinates, the even number of them, such that given contact form we started with has this canonical expression as on the jet bundle. So again, locally all contact distributions look like Cartan distributions on the first jet of sections, but this is local. And also as a consequence, all not only the form looks like that, but also we can always find vector fields that span our contact distribution that also look in this canonical way. And there are two other important notions that are associated with contact distribution. First is so-called Riemann vector field. Here is the Professor Riemann. In my opinion, his facial expression is a little bit silly, but even professors can be a little bit silly from time to time. So what's the Riemann vector field? The definition is written here. It is a distinguished, if we have a fixed contact form, it may be local, but we have it fixed. Then the Riemann vector field is something, it's a vector field that lies in the kernel of the differential of eta.
Actually, if I may please.
Yeah.
I think that it's supposed to be pronounced red.
Red.
Yeah, it comes from red.
Really?
Yeah, red.
Yeah, okay. So, together with Eresman, we are in the Jewish cultural circle.
Yeah, I mean,
okay.
It is a bit of very close.
Yeah, sorry. I feel corrected. So we have the vector field which lies in the kernel of the eta, which definitely means that it is not in the distribution itself. So this selects as, say, the direction of this vector field, and it is not enough to know the direction. We still have to fix a scale, so in a sense a length of this vector field, and the scale is fixed by stating that while contracted with contact form itself, it should give 1. And we can easily see that in the Book coordinates, it is just a vector field in the direction of z coordinate. As we can see from the definition, it severely depends on the choice of the contact form. And we already learned that usually it is not chosen once and for all. There is a certain ambiguity in this choice. So also red vector field is not chosen once and for all. And this dependence is really severe because when we multiply our contact form by a function, this red vector field changes completely together with the direction. It is not like that it only scales. It also changes the direction. And it can be proven that if we take whatever tangent vector which does not belong to the contact distribution, this tangent vector can be a value of some red vector field for some contact form. So we can always choose a contact form in such a way that this one particular vector will be the value of the red vector field as this particular form, at this particular form. However, even if this dependence is very strong, it is in a sense a canonical object, and it is very deeply studied in differential geometry. For example, there is a class of contact manifolds that are compact. So for compact contact manifolds, we have a conjecture formulated by Alan Weinstein that in each such a case, red vector field has at least one closed trajectory, which means that, of course, this trajectory has to be a circle or something like that. And it is proven in several concrete examples. For example, definitely it is true for S3, because then all of those trajectories are circles, and these are fibers of the Hopf vibration. In other cases, it is not proven. So it is, if somebody wants to solve something serious, one can tackle this problem. However, I must warn you that the literature is really huge about that. people were thinking about that, and there are many partial results. To my knowledge, no global result at the moment. There are partial results, for example, in fixed dimensions and whatever. So this is one notion, and I should probably go to the finish. I have started 5 minutes after, so do I have 5 minutes? Okay. So let me then introduce another notion that will be very important for our second lecture, contact Hamiltonian vector fields. And this is the notion that we will be thinking of probably to the very end of the lecture, because they're useful tools, those contact Hamiltonian vector fields. As you can see, the definition is a little bit similar to the symplectic Hamiltonian vector fields. So let us fix a function. Sorry, it is not on R, it is on M, of course. A function on M, on a contact manifold. We fix a function on a contact manifold, and we produce a vector field on a contact manifold out of this function with the following two conditions. First condition a little bit resembles the definition of the symplectic Hamiltonian vector field, in a sense that vector field contracted with some 2 form is a differential of the function. However, there is some complement here. So not the differential, but differential plus something. And as we know, the differential is not degenerate only on contact distribution, but in the whole tangent bundle it is degenerate. So this first condition is not enough. We have to add something, and what we add is the condition, again, the scale. So vector field, contact Hamiltonian vector field, contracted with the contact form, gives us Hamiltonian up to a sign. And those two conditions define Hamiltonian vector field uniquely, as we will see while, for example, calculating in coordinates. Such a vector field is called a contact Hamiltonian vector field. This adjective should distinguish it from symplectic Hamiltonian vector field. So what are the problems with this Hamiltonian vector field? Since I have a few minutes left, I will not go into the calculation now. I will only maybe go through the problems, and then we can come back to the calculation and look and see how those problems arise. So first, a definition of a contact Hamiltonian vector field is local. Since in general contact forms are local, then Hamiltonian vector fields are also local. So the first question we might ask is whether there are global Hamiltonian vector fields, whether we can construct. And the answer is yes, there are. Even on Mobius strip, we can get a global Hamiltonian contact Hamiltonian vector. The one way of constructing this could be if, for example, if changing the form does not change the vector field, yeah? And this is not the case. I mean, if we keep the Hamiltonian and we fixed and we change the contact form, the Hamiltonian vector field changes. If we want to keep the Hamiltonian vector field fixed, then we also have to change the Hamiltonian, and it appears that we have to multiply it by the same function, which is quite easy to guess, but not that easy to prove. It is a piece of calculation that you would probably want to delegate to your students rather than do it yourself, but it is doable. And then there is this third problem, which comes from the calculation I didn't show you, that while Hamiltonian vector field preserves the contact distribution, it is a symmetry of the distribution, it is not the symmetry of the contact form. So we would like to know we would like to have a better language to describe Hamiltonian vector fields in a way that we would understand the relation between Hamiltonians and Hamiltonian vector fields better without doing tedious calculations, and to really be able to define them without using the contact form, which is local. And this is the task for the next lecture. Thank you very much for now.